galvanometer. So it's a galvanometer. Then there are two types of galvanometer will be there. One with zero deflection at the midpoint, and where the zero will be your left end and zero will be the midpoint of the scale. What is a basically galvanometer? Again, it contains like it's a device used to measure the magnitude and direction of current. What actually galvanometer made up of? So it will be made up of like a current carrying loop. One loop will be there, a magnet. Then when you pass a current through that loop, it will get deflected and a torque due to dipole moment will be set up. So all this will come in construction of galvanometer when we go for in the magnetism chapter, electromagnetism chapter. Dipole moment when we discuss, no, there will go in detail working of galvanometer. Okay, no, time being. So if it is having a scale like 0 to 10 milliampere, what do you mean by that? If you send a current of 5 milliampere, the deflection will be at 5 milliampere, the pointer. If you send 2 milliampere here, the pointer will be at 2 milliampere. If you send 10 milliampere, the pointer will be at 10 milliampere. Then the pointer means that this one, like we can have a pointer here. So it will deflect. So when you send 1 milliampere, 1 milliampere, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliampere you send. If you send 15 milliampere, the pointer cannot deflect more than 15 milliampere. Able to notice out? And I'll take some. Yeah, this will be the pointer. So the pointer, what in fact is going to deflect it. As you pass current, the pointer is going to deflect here. So what is the maximum deflection I can get it? 10 milliampere. The deflection more than 10 milliampere not possible because there's a maximum current the galvanometer can withstand. Okay, that particular current we'll call that as high G, or current for which the deflection galvanometer will be maximum. Then this galvanometer made up of many conducting parts, so it will offer some resistance. That all resistance of galvanometer, I'll call it as galvanometer resistance. Okay, now come for this one. Now we have another type of galvanometer. Yellow color. Let me take green color. We have another type of galvanometer where when no current flows, the pointer will be at 0. The 0 of galvanometer will be the midpoint of a scale. So if you send current in one direction, the deflection will be on one side. If you change the direction of current, the pointer will deflect on either side of 0. So here, so this galvanometer, what will happen, will measure the magnitude of current and also the direction of flow of current. Agreed this? So for such a galvanometer to indicate direction of current, the pointer, the 0 should be at the midpoint of a scale. So if your current flows, if current flows to galvanometer in say like a towards right, deflection will be on this side. If current flows in opposite direction, the pointer will deflect on either side of 0. In this way, the pointer open will deflect on either side of 0 based on direction of current. Okay, these are basically two types of galvanometers are there. So here I can even predict the direction of current, whereas here only magnitude of current. Here direction as well as magnitude. Agree this? So now in the Wheatstone network, I am going to connect a galvanometer which will indicate the direction of flow of current and also the magnitude. I'm more bothered about the direction, where the 0 will be at the midpoint of a scale. Okay, now I have 4 resistors. So these are the known thing. P, Q, and S are known. The unknown resistance is what I'm going to connect here. So what is this one? Why do we use Wheatstone network? To find out the resistance of any wire or a body. So I'm going to connect in this branch. I'm going to call this as a branch. AC is one branch, CB is one branch, BD is one branch, and AD is one branch. The unknown thing, I'm going to connect it here. This unknown thing. Okay, these things are the known for us. These branches are known. I can adjust the value of S. Variable, I can adjust the value of S till the deflection the galvanometer will be 0. Okay, no. What is our primary question? How to find out this unknown resistance? No? How to find out this unknown resistance? Okay, now let's see like if VC equal to VD. When this will happen? when current through galvanometer is 0. How to make current through galvanometer 0? The unknown resistance is connected. I'll adjust the value of S in such a way that the current through galvanometer is 0. How to check it's a 0? First, certain values of S, the pointer will be on the right side of 0. For certain values of it, the pointer will be on the left side of 0. Exactly, I'll adjust the value of S at one point. The pointer will be the pointer will merge with the 0. I'll see that no parallax will be there. Then current through galvanometer is 0. Then potential at C should be equal to D. Because if current 0 means no potential difference should occur, because current flows from high to lower potential. If there's no flow of current here, then these two should be at same potential. So VC equal to VD, I'll get it. Then can we write it? VAC is equal to VAD, because A is a common point. VAC equal to VD. What is VAC? Applying the loop equation, applying the KCL. So it will be like VA minus I1P minus VC equals 0. So then what is VA minus VC? Equal to I1P. So this will become VAC. Similarly, what is VAD? I'll write down the loop equation. VA minus I2R minus VD equals 0. So VAD is equal to I2 into R. Where you begin positive and where you end up, there should be negative. So I'll move from positive to negative. So this will be the polarity, no? If a current enters, there should be positive. Where current leaves should be negative. So VA minus I1P minus VC equal to 0. Solving this, we'll get VAC equal to I1P. Similarly, VA minus I2R minus VD equal to 0. Then VAD equal to I2R. So let me substitute VAC equal to I1P here. VAD equal to I2R. So the ratio of I1 by I2 should be equal to R by P. Call this equation 1. Similarly, we'll write equation for VCB. Let me write that loop equation here. Now what is VC minus I1Q minus VB 0. Then VC minus VB equal to I1Q. Then VD minus I2S minus VB0. So VD minus VB is equal to I2 into S, or this is nothing but VCB equal to I1Q. This is VDB equal to I2S. Let me come for this one. VCB should be equal to VDB because VC equal to VD. So I agreed. So then what is VCB? All these things I'll highlight it, which I'm going to substitute. Okay, look at this one. So what is VCB equal to I1Q? What is VDB equal to I2S? So I1 by I2 equal to S by Q. I have two equations, 1 and 2. Let me divide these two. I1 by I2, I1 by 2 will get cancelled out. So what do we end up? R by P, or I'll equate R by P should be equal to S by Q. Then I'll rearrange. If I rearrange, the R is unknown, no? So R is equal to P. So R is equal to how much will be like a P by Q into S. This is the Q. So there's an expression for the unknown resistance. So like this, the unknown resistance we are going to calculate here. Okay, now. So if a resistor, if there is a, what we can do that one. So here this same potential, you can remove this galvanometer. When you remove it, you'll get a situation of like this. Then if I ask you to find the effective resistance, so PQ in series, the effective of that P plus Q will be in parallel with R plus S. Like that, we can simplify the network also. The unknown resistance which we are supposed to find out is that we have determined. Look at here. So when bridge is balanced, balance sense current through galvanometer will be 0. When the bridge is balanced, current through galvanometer will be 0. Okay, look at a condition now. So I have brought one simple case. I can interchange the position of galvanometer and cell. I can interchange the position of galvanometer and cell, you can see. Still, the ratio of P by Q equal to R by S will be valid. So again, here like a VAB will be at same potential. Okay, let's do one thing. VA equal to VB. If VA equal to VB, then what you are going to write? Q by S should be equal to P by R. Solve it. Similarly, VA equal to VB. If VA equal to VB, here also again the same condition. So if the bridge is balanced, you can interchange the position of the cell, or you can redraw the circuit here. You can redraw the circuit, we'll get the condition of like this. Where the galvanometer is connected between A and B. I'm just redrawing you, see that one. When I redraw the circuit, will come like this. Either even here also you can apply the same condition, Q by P equal to R by S. Okay, now other forms of Wheatstone network. If you have like this here, so the R is unknown thing. This is some resistance you can pick up here. Now look at this. There's a network. I'm asking you to find the effective resistance RAB. That was my question. How to find out here? How to find out that one? So here, what I suggest is like just redraw the circuit and make it in the form of like Wheatstone network. So between A and C, a resistor P is there. Between A and C, resistor P is there. Between C and B, a resistor Q is there. A resistor Q is there. Between C and D, a resistor G is there. Between A and D, a resistor R is there. Between D and B, a resistor S is there. So then current through galvanometer, also like this will be when the bridge is balanced, when P by Q equal to R by S, you can remove this one, no? So this resistor can be removed. When you remove that, how it will appear? P by Q equal to R by S because of this condition. Why you are removing? Because if condition satisfied, P by Q equal to R by S, then only you can remove this galvanometer. Then potential at C equal to potential at D. Then if any resistor connected across equipotential points, the resistor should be removed. The resistor can be removed because there's no current through the no current through this resistor. No current flows through this resistor. So therefore, even if its presence or absence, what happen will not disturb the current flowing through these branches here. Okay, now what is the resistance now? P by Q, this is in series, R by S, this is in series. The effective resistance, solve it, we'll get the required answer. Like that, we can find out the effective resistance across AB. So we can't find out by any other method. Any other method will be very lengthy. Just convert this of the form of Wheatstone network and redraw the circuit, you'll be in a better position. Once I know the resistance, this one, can I measure its resistivity? Yes, I can measure the resistivity or conductivity, what you can call. The resistivity will be unknown quantity to this resistivity of material will be very difficult quantity to measure. Yes, with the help of this, I can easily find out now the resistivity of this material which is connected here. This is unknown thing. Okay, this is the main purpose of the Wheatstone network. To find out the resistivity of material, we take help of Wheatstone network. Whatever the primary idea of this is, like the Wheatstone network, it was designed by some like a botanist person who was working agricultural engineer. He was nowhere related to physics. He wanted to measure the fertility of soil. To measure the fertility of soil, what happened? We use this Wheatstone network. There's a major advantage of this one. To measure fertility of soil, Wheatstone network is used. Okay, this was designed by some botanist, not something engineer. He was a botanist. He wanted to know the fertility of soil. So a soil, fertility of a soil depends upon the resistivity of the soil. So by making the resistivity of soil, we can check like what is the fertility of soil. I think all of you know fertility, why you need, because I think when you sow seeds, what be the, when we sow a seed, how the crop, what amount of crop will get per hectare, I think that depends on fertility, no? So definitely what happened? So I wanted to know the fertility of soil. So the soil which I wanted to measure fertility, I'm going to keep it in a box here. Then I have a setup. Then I'll measure the resistance of that soil, and I know what is the length of the soil in the form of a cylinder I'll be using. I know length and area of cross section. I know resistance are. Then I'll get the resistivity. From resistivity, I'll come to know, I'll get the fertility. Then I can advise to the farmers like, this is the fertility of this. So your efficiency of crop will be this much if you going to sow a seeds now. What further has to be done to increase the fertility, I can give advice. There's an advantage of these things. See, the entire engineering is